variations on a theme. So Meltdown is also known as variant 3 of the original set of vulnerabilities that came out at the beginning of last year. Some processors will allow speculative reads of system registers that you shouldn't have access to. And again, similarly to Meltdown, it will get caught, it'll get tagged for an exception, and what should happen is the program should never observe anything that happens after that point. But for a brief period of time, speculation will continue until it's undone. And you can perform similar cache accesses to read the content of some registers that you're not supposed to have access to. Another one that we had last year, speculative store buffer bypass. In modern processors, we have an optimization, often called memory disambiguation, where when we perform a load, when we read some value from memory, we have to search to see if we did a recent store, if we recently wrote something to that same memory location, right? Because if we did, if we write something to memory and then we read back, we really, really want to read what we wrote, okay? But we want to have an optimization here for performance to say it's unlikely that we're going to read from exactly the same location every time, right? So why don't we just keep going? And in parallel, we can go and see, does our store buffer contain a recent write to that same memory location? And if it does, we're going to have to kill what we did because it turns out that the value's been updated and we should have used the updated value. But again, there's a small window where we can mis-speculate based on the idea that that value has not been updated. And so this can be exploited to see older values that we should not have access to. And in particular, this can be used to exploit JITs and sandboxes to nefarious end. Yeah, so we have mitigations we can use for this. There's some interfaces we've added that basically allow us to turn off memory disambiguation or speculative store buffer bypass, as we call it. Has a performance hit. It's about a 10% performance hit, but we need to do it. For example, in the case of a Java workload that we don't trust, because it turns out we can exploit this, for example, to see what other processes running within that same Java sandbox are doing. Another vulnerability we had, lazy floating point save restore. So particularly x86 processors, based on the history of how they implemented the floating point unit, there's this concept of a floating point disable, where I can say, don't allow access to the floating point unit. And the reason I do this is when I'm switching from one application to another, it's quite likely that not every program is using floating point math. So I can lazily save and restore the floating point state. In particular, if one process is doing floating point and no other process is, well, I just disable access to the floating point unit when I switch to another process. When I come back to the old process, I'll re-enable it. The problem with that is, if I can speculatively access floating point registers using a similar trick to Meltdown, then I could see, for example, crypto vector operations that are happening by another process. There are some variants on the original Spectre variant 1. There's a store variant that's very similar. That's called variant 1.x. There's another attack on the TLBs themselves. I can actually perform a timing analysis over time as TLBs get populated. I can monitor those, it turns out, and I can use that to infer certain information about cryptographic operations. Some of the vulnerabilities rely on exploiting SMT or hyperthreading, which is, as I said, when you partition cores and you actually make it look like you have more than a single core by partitioning and dividing out those resources. But because you have very tight sharing of the underlying resources within that processor core, one thread can actually infer various things about what the other thread is doing. And in particular, for TLBleed, I can exploit that to monitor the operations performed by the other thread. There's also the SpectreRSB, or the return stack buffer exploits. As I mentioned before, I predict which way I'm going to return whenever I'm making function calls and returning. Well, it turns out that if I make a function call, make a series of function calls, push things onto this return stack, but then I don't actually return, I just make a jump somewhere else, I can actually end up with an imbalanced return stack. And again, I can exploit that to have the processor mispredict where functions are going to return from. So here's an example of how that would happen. I can also do Spectre over the network. So there's a way that I can effectively mistrain the branch predictor by sending very carefully crafted packets to a remote machine. Those packets are going to mistrain the predictor so that later on, another piece of code, when it runs, is going to leak something based on whether a value was loaded into the cache or not. And it turns out I can do remote timing analysis. It's fine-grained enough that I can do this over the network. The researchers who came up with NetSpectre were able to achieve a bit rate of something like 6 bits per hour, something like this. It's not exactly very efficient, but if you just want to reveal a secret key, you don't actually need to have that many bits. Another vulnerability, L1 terminal fault or Foreshadow, exploits what happens when we walk through page tables and handle address resolution. So this is one of the Foreshadow discoverers. I've been doing a world tour over the past year, taking selfies with some of these folks. Oh, and on the left there, that's the first time I got it working. I was sitting on a plane over the Atlantic, and I think I might have exclaimed some expletive very loudly on the plane when I got it working. So this is basically a virtual machine being able to read physical memory from the underlying host, which obviously should not be possible. And what happens is, when I'm performing an address translation, as I mentioned, I go through these multiple different stages, and ultimately I determine, do I have a valid translation or not? And if I have a valid translation, what I should do is forward that to my cache and say, do you have the data that I'm looking for, or do you need to load it? But there could be speculation there. I could speculate that the address that I'm sending is valid before I've fully resolved whether that's the case. And it could be doubly worse in the case of a hypervisor. If I forward this address and skip the second stage of translation. So for example, in the case of L1TF or Foreshadow, I can write malicious code that marks a translation as not present or invalid. And what the processor will do is it will say, well, I'm going to kill this anyway because this is not a valid translation, but it will continue to run just a few instructions before it actually kills code that speculates beyond this point. And it turns out, in that small window, data that I load may see only the first stage of translation. So now I'm going from inside my virtual machine, now I'm seeing addresses that are being treated as host addresses and not translated the second time. So I can do what looks like a meltdown attack, and I can dump memory from the host system. So there's some more data here you can read in the slides about how that works. I think I'm going to skip through that one. There's another attack called PortSmash. PortSmash is about realizing that we have these hyper-threaded processors with shared resources inside the core. And by carefully monitoring, by writing careful code running on one thread and being aware of how that will execute, I can actually infer what the other thread is doing based on the underlying resources, the execution ports inside that core.